So today we are going to talk about a new topic called as moment of inertia. Okay, so now what is this moment of inertia and where does it come from? To understand that, let's talk about kinetic energy of a rotating body. Okay, so suppose this is a rigid body and it is rotating with some angular velocity omega bar about this shown axis. So now we know that when this body rotates about this axis, what will happen? Different particles of the body, they will perform circular motions, right? So suppose this particle whose mass is m1, it revolves in this circle and this circle has radius r1. This particle whose mass is m2, it revolves in a circle of radius r2. Okay, so now their kinetic energies would be different. Okay, kinetic energies of different particles would be different. So if we add up the kinetic energies of all particles, then what do we get? We get kinetic energy of the body. Okay, it's very simple, right? So suppose m1 is mass of first particle, it revolves in this circle of radius r1, okay, when this body rotates, and its velocity is v1. So now we know what is v1. v1 would be equal to what? r1 times omega. Okay, similarly v2 would be equal to r2 times omega, v3 would be equal to r3 times omega. Omega would be equal for all particles. Okay, all particles move through same angle in same interval of time, right? Okay, otherwise some particles will move ahead and some particles will be left behind. So that should not happen. So omega has to be same for all particles. So now kinetic energy of first particle is half of m1 v1 square, kinetic energy of second particle is half of m2 v2 square, so on and so forth, up to kinetic energy of nth particle is half of mn vn square. And if you add up all these kinetic energies, then you get kinetic energy of the body which is rotating, right? So it is half of m1 v1 square plus half of m2 v2 square plus so on and so forth up to plus half of mn vn square. This is kinetic energy of the body. Okay, so then if you substitute v is equal to r times omega, then we get half of m1 into r1 omega square plus half of m2 times r2 omega square plus so on and so forth, half of mn multiplied by rn omega square. Okay, and in this thing what we can do is we can take half and omega square common, right? If we take half and omega square common, so what do we get from here? m1 r1 square, right? It will be square of r1 and square of omega. So m1 r1 square from this term, m2 r2 square from this term, so on and so forth, and in last term, from the last term you get mn rn square. Okay, so you have half of m1 r1 square plus m2 r2 square plus so on and so forth up to mn rn square multiplied by omega square, and this term can be written like this, okay, in compact form, like summation of I goes from 1 to n, summation of mi ri square. Okay, I goes from 1 to n, summation of mi ri square, right? So this thing is called as the moment of inertia of the body. Okay, this term is known as the moment of inertia of the body, and we denote it by letter I for inertia. Okay, so kinetic energy of a rotating body can be written as what? Half of I omega square. And what is I? It is summation of mi ri square. I goes from 1 to n. Okay, so this thing is clear. Is this thing clear? Everyone? Right. So now we found that kinetic energy of a rotating body is half of summation of half of I multiplied by omega square. That is kinetic energy of the body. And what is I? It is called as moment of inertia. It is denoted by this thing. It is half, not half. It is equal to mi ri square. I goes from 1 to n, right? So now this moment of inertia, okay, kinetic energy of rotating body can be written as half of I times omega square. Now if you compare this with kinetic energy of a linear body, it's given by half of m multiplied by v square. Okay, so omega in rotational motion is analogous, means it's similar to V in linear motion. Then if you compare the formula of kinetic energy in linear motion and kinetic energy in rotational motion, then you get that the mass in linear motion is analogous to I in rotational motion, and the mass gives measure of inertia in case of linear motion. That means I must give the measure of inertia of a rotating body, right? Okay, is the connection clear? See, V is analogous to omega, or omega in circular motion or rotational motion, it is analogous to what? V in the linear motion. Okay, then if we compare the formula of kinetic energy of linear body or body which is moving in linear motion, not linear body, body is moving in linear motion, and body which is moving in circular motion or rotational motion, not circular, rotational motion. So then what do you get? Omega is analogous to V, so I must be analogous to M, so I must be similar to M. Okay, so as M, mass represents the inertia of a body in linear motion, just like that I, that is moment of inertia, represents the inertia of a rotating body. Okay, is it clear? Yes, no? Right. So then now we can see some simple examples. So moment of inertia of a system which is shown in this figure. So what is this system? You have two masses, okay, two objects, two balls you can say, having mass m1 and m2, and they are connected by means of a light rod. Okay, so it doesn't have any mass. Let's assume that the rod doesn't have any mass. Then use the formula. What is I? It is summation of mi ri square. So for first particle is at distance of L by 3 from the axis of rotation. Second particle or second mass, you can say, it is at distance of 2L by 3. Okay, masses are m1 and m2. So what would be the moment of inertia? I is equal to m1 multiplied by this L by 3 square plus m2 multiplied by 2L by 3 square. That's very simple. And suppose m1 is equal to m, m2 is also equal to m, the two masses are equal, then you substitute for that and you get L by 3 square is L square by 9, 2L by 3 square is 4L square by 9, and if you add it up you get 5 ml square by 9. So this is moment of inertia of this system, right? So this is very simple. Okay, so this is how we apply this formula. Okay, this is clear. Okay, good. Then now this is a moment of inertia of a system having discrete masses. Okay, this is moment of inertia of a system having discrete particles. If you have countable number of particles, then you can use this formula, summation of mi ri square. If you can count I is equal to 10, I is equal to 100, right? In this case, I is just equal to what? 2. I goes from 1 to 2 only. Okay, so then you can use that formula. But as we discussed in the earlier cases also, we cannot measure the number of particles in real objects, right, in continuous mass system, right? So for an example, in case of this pen, you cannot measure how many number of particles are there, right? So in such cases, what we do is we make use of integration. So again, we divide the system in n number of small segments, and suppose this is small segment, this is small piece having mass dm and its distance from the axis of rotation is r. Then what would be the moment of inertia of this mass only? The moment of inertia of this mass only is dm multiplied by r square. Okay, now suppose I want moment of inertia of this complete body about this axis of rotation. What should I do? I should take small pieces like this. Okay, I should find out their moment of inertia and I should add it up. Okay, and that whole procedure is known as what? Integration. Okay, so for this mass we have moment of inertia is equal to di is suppose moment of inertia of this much mass only, and that is r square dm. Okay, distance of this mass from the axis of rotation is r. Then moment of inertia of this whole body is given by just integration of this di. Okay, the integration of r square dm, right? So then we can apply it. So we apply that for a thin rod. For an example, you have this pen. Okay, it's like a uniform thin rod. Okay, so suppose I want to find out its moment of inertia. What should I do? And now this moment of inertia will be axis dependent. So suppose I want to find it for this axis which passes through its center or its center of mass, that is its midpoint. Then now this much distance would be L by 2 and this much distance is also L by 2. So if I call this point origin, okay, that is 0, then the rod is kept on the x axis and you want to find its moment of inertia about the y axis. Then this point is minus L by 2, right, and this point would be plus L by 2. Okay, so then what we do is, in this case, this is a linear object. This is a linear object. So we define linear mass density of this object. So what is linear mass density? It is mass per unit length. Okay, so linear mass density is mass per unit length. Okay, so then now if I take small piece of this object, so suppose I take small piece having length dx, its mass is dm, and its distance from the axis of rotation is suppose x. Then what would be moment of inertia of the small object, small piece? So it is just dm, the mass, multiplied by distance square. Okay, its distance from axis of rotation is x, so dm multiplied by x square, right? So that is moment of inertia of the small piece, small segment, you can say. So di is the moment of inertia, it is dm multiplied by x square, right? So now we define linear mass density, that is mass per unit length. So mu is mass per unit length. So for this object it will be dm divided by dx. Now I want to write dm in terms of x. So what I will do is I will take this dx on other side. So I can say that dm is equal to mu times dx. Okay, dm is equal to mu times dx, right? You put that here and then you integrate it. Okay, so why did we do this? Because here there were two variables. Mass is a variable and x is also a variable. We want to connect them. We want to have only one variable. Okay, so we wrote mass in terms of x, right? So di is equal to mu times dx multiplied by x square, and then you integrate it. You integrate it from minus L by 2 to plus L by 2. Okay, you integrate it from minus L by 2 to plus L by 2, and then what do you get is, so if you integrate that, put the values etc., then finally you get I is equal to ml square divided by 12. Okay, so do I need to explain this derivation? Yes, no?
So,
Okay, so suppose you can take this mu outside. You are integrating mu x square dx. You can move mu outside. So what you get is x square dx. Okay, you are left with x square dx. You integrate that, its integral would be x cube divided by 3, right? Because we know integration of x raised to n dx is x raised to n plus 1 divided by n plus 1 within proper limits, some lower limit, some upper limit. So here the lower limit is minus L by 2, upper limit is plus L by 2. So you integrate it from minus L by 2 to plus L by 2, right? So you put the upper limit then and the lower limit. So when you put upper limit, x becomes L by 2 cube, then you put negative sign and put the lower limit. So x becomes what? Minus L by 2. So minus L by 2 cube, right? You take this 3 outside. Okay, and what is mu? So mu is equal to mass divided by length, m upon L. Then now what is L by 2 cube? It is L cube divided by L cube by 8. Okay, L by 2 cube minus, you have minus L cube by 8. So that minus minus becomes plus. So L cube divided by 8 plus L cube divided by 8 is 2 times L cube upon 8, or you can say it is L cube divided by 4. So L cube divided by 2L cube divided by 8 means L cube upon 4. Now this cube gets cancelled with this L and you have L square left. Okay, so it is ml square divided by 4 times 3 means ml square divided by 12. Right? This is clear? Yes, no? Okay, so now this is just to give you an example of how does this formula work, how do we take integration, etc. So then there are several bodies, okay, several objects. For an example, you have this thin ring. So moment of inertia of a thin ring having mass m and having radius r is just equal to mr square. Okay, because for a ring you can say whole mass is at the same distance from the axis of rotation. So if you take mass over here, mass over here, mass over here, then its distance from the axis of rotation is equal, right? So what is di? It is moment of inertia of this much mass, okay, dm. It is dm multiplied by r square. Now if you integrate that, if you integrate di, then what do you get? It's integration of dm times r square. You can move r square outside because r is equal. Wherever you take that small piece of mass, okay, small piece of the ring having mass dm, its distance from the axis is equal, right? So you can just move r square outside and integration of dm is just total mass of the ring. So that is m, okay, and that's why you have r is equal to mr square, right? This is clear? Everyone? Okay, good. So now this is how we can find out moment of inertia of various objects, various bodies. So at this stage you need to just remember the formulae, okay? You can still understand, but you need to remember the moment of inertia of various objects. So there would be a list. There is this list, okay? For uniform thin rod, the moment of inertia about an axis passing through its center, that means its midpoint, and perpendicular to its length, the moment of inertia, we just found this, it is ml square divided by 12. For an axis which passes through its edge, okay, axis like this, moment of inertia is ml square by 3. Okay, then for a ring it is mr square. For a ring or a hoop, moment of inertia about an axis passing through the center, it is equal to mr square. Okay, for a disk, moment of inertia about an axis which passes through its center perpendicular to its plane, okay, for a disk it is mr square divided by 2, right? Then for a hollow disk, it is, so hollow disk will have two radii like this. So this is inner radius, it's r1, outer radius is r2. Then its moment of inertia is just m multiplied by r1 square plus r2 square divided by 2. Then for a hollow cylinder, the moment of inertia, it is mr square. For a solid cylinder, this is a solid cylinder, okay, about an axis which passes through its natural axis, you can say, it is mr square divided by 2. For a hollow cylinder, it's mr square. For a solid cylinder, it is mr square divided by 2. Then for a spherical shell, means hollow sphere, the moment of inertia about an axis passing through the center is 2 by 3 mr square. And for a solid sphere, the moment of inertia about an axis which passes through its center, okay, it is 2 by 5 mr square. It is 2 by 5 mr square, right? So you need to remember these formulae. For solid sphere, it's 2 by 5 mr square. For a hollow sphere, it is 2 by 3 mr square. Okay, so list is given and we need to memorize those formulae. So this is clear? Yes, no? Okay, so then let us solve some simple problems based on moment of inertia. So let's see this one. A circular disc is to be made by using iron and aluminum so that it acquires maximum moment of inertia about a geometrical axis. It is possible with option A, aluminum at interior and iron surrounding it, iron at the interior and aluminum surrounding it, using iron and aluminum layers in alternate order, and sheet of iron is used at both external surface and aluminum sheet as internal layers. A circular disc to be made using iron and aluminum so that it acquires maximum moment of inertia. Tell me. You want to make a disc, okay, using iron and aluminum. So this one is a disc made up of iron and aluminum. Okay, and you want its moment of inertia to be maximum. So then should you keep aluminum at interior and iron surrounding it, or otherwise, that means iron at interior and aluminum surrounding it, so that you have maximum moment of inertia? What is the formula of moment of inertia? It is integration of r square dm, right? Or you can take this formula also, just to imagine. You can take summation of mi ri square, and you want this to be maximum. Tell me. You want more moment of inertia, means heavier of the two, okay, that is iron, should be away from axis of rotation. Right? Yes, no? More mass should be away from axis of rotation. Okay, then the moment of inertia would be greater. So what's the answer? Aluminum should be at the interior and iron should be surrounding it. Okay, this is the answer. Right? Okay, so that is very, very simple. Let's see next question. A flywheel rotating about fixed axis has a kinetic energy of 360 joule. Okay, so kinetic energy is given. It's 360 joule when its angular speed is 30 radians per second. Then the moment of inertia of the wheel about the axis of rotation is. So very, very straightforward question. You have E equals to half of I omega square. We know this formula. Okay, we just saw this kinetic energy of a rotating body. The moment of inertia. Okay, right, moment of inertia. So to find out moment of inertia, take omega square on other side. So what do you get? You get I is equal to 2 times of E divided by omega square. Okay, 2 times of E. What is E? E is 360, and omega. What is omega? Omega is 30. So 30 square. Is it in proper units? It's in proper units, right? Unit of omega is radians per second only. So 30 radians per second. So let's check. So it is 30 times 30 square, right? So that's 900. So 2 times 360. So then 36 divided by 9 is 4. 4 times 2 is 8. But it will be 0.8, right? Yeah. So Nikita is correct. It's 0.8 kg meters square. So it's option C. So very simple question. Okay. Direct question. Right. This is simple. Yes, no. Okay. Let's see next one. Three particles each of mass m gram are situated at vertices of equilateral triangle. Okay. This is an equilateral triangle and you have three masses. Okay. Three particles having masses m only, right? M. They are at the three vertices of an equilateral triangle as shown in this diagram. So triangle ABC of side L centimeter. Okay. The moment of inertia of system about the axis about a line AX perpendicular to AB. So it is AX perpendicular to AB and in the plane of ABC, in plane of ABC. So that line is in plane of ABC, that's given in gram centimeter square. So in the same units, right? So masses are given in gram, distances are given in centimeters. So unit of moment of inertia would be gram centimeter square. So let's find it out. Okay, so let's call them M1, M2, M3. So suppose this is my M1, this is M2 and this is M3, right? Then let's use the formula. So moment of inertia I would be equal to M1 R1 square plus M2 R2 square plus M3 R3 square. So that is, what is M1? M1 is M. What is its distance from the axis of rotation? No distance. So it is equal to 0, right? Plus M2, M2 is also M. What is its distance from the axis of rotation? Tell me if this is an equilateral triangle. Then if you draw a perpendicular from here, it meets this base. Where does it meet? What should be a distance of this point from A? Let's call the point M. Yes, this distance should be equal to, it will bisect this line, no? So this distance has to be equal to L by 2, right? L by 2. Okay, so this is L by 2. So M multiplied by L by 2 square plus then third mass, it is at distance of L only. So ml square, right? So it is ml square by 4. L by 2 square is L square by 4 plus ml square. So that is equal to, so this thing can be written as 4 ml square divided by 4 because we want to make the base same, denominator same. Okay. So ml square plus 4 ml square means 5 ml square. 5 ml square divided by 4 is the answer. Okay, so it is option C. Right. So this one is also simple, just some calculation. Okay. Right. So these are basic questions based on basic topic. Okay, let's see next one. A light rod of length L has two masses m1 and m2 attached to its two ends. The moment of inertia of the system about an axis perpendicular to the rod and passing through the center of mass is. Okay, so you have two objects, a light rod of length L. So rod is massless and two masses m1 and m2 are attached to its two ends. Okay, then the moment of inertia of this system is, this is the question. Okay, now let's solve this one. So we'll solve this one, but then result will memorize. Okay, this result we are going to memorize. All right, so you have two masses at the two ends of a light rod. Okay, and suppose its moment of inertia, we want to find out its moment of inertia about an axis passing through the center of mass. So you can say this point is C, the center of mass. this is m1, this is m2. Okay, so now how will you find out center of mass? Suppose I want to find out distance of center of mass from m1. Okay, so that distance is L1. Let's say this distance is L1. So if I take origin at m1, then I can find out L1. L1 would be equal to what? It is equal to m1 times 0 plus m2 times L divided by L1 plus L2, or m1 plus m2, right? m1 plus m2. Remember the definition of center of mass: m1x1 plus m2x2 divided by m1 plus m2. Yes, no? Remember or you don't remember? Okay, so it is m2 times L divided by m1 plus m2, right? Then distance of the center of mass from m2. So suppose this is L1, this is L2. What would be L2? So similarly, I can say that L2 would be equal to m1 times L divided by m1 plus m2. Okay, so you start measuring the distance from this point, suppose. Then what would be the distance of center of mass? Then you can say m2 times 0 plus m1 multiplied by its length, okay, divided by m1 plus m2, right? This is clear? Yes, no? Okay, I just want the length. If you want the coordinate, so suppose you call this origin, then center of mass would be towards left. So that will come out to be negative. But I don't want that. I just want this length. So L2 is equal to m1 times L divided by m1 plus m2. Then what would be the moment of inertia of the system? So moment of inertia is just moment of inertia is m1 L1 square plus m2 L2 square, and that is equal to m1 multiplied by what is L1? So L1 is m2 times L divided by m1 plus m2 square, right? Plus you have m2 multiplied by L2 is m1 times L divided by m1 plus m2, and you have square of that. Then we can take it square. So then what do we get? Take it square. Okay, so it will be m2 square. So this thing is m1 multiplied by m2 square L square divided by m1 plus m2. Okay, plus again you have m2 multiplied by m1 square L square divided by m1 plus m2, right? And then you can take L square common from these two. m1 plus m2 you can take common, right? And again m1 m2 also you can take common. Oh, in denominator it will be square of this thing, no? m1 plus m2 square. So if I take m1 m2 common, okay, then from the first term I will have m2, and from the second term I will have m1, right? If I take m1 m2 common, then from the first term I will have m2, from the second term I will have m1, and this everything multiplied by L square divided by you have m1 plus m2 square. And then this m1 plus m2 and in denominator the square gets cancelled out, and you get this formula m1 m2 divided by m1 plus m2, okay, multiplied by L square. And this thing m1 m2 divided by m1 plus m2, we call it as a reduced mass. Okay, we saw this in case of collision also, right? We discussed collisions, then also this term came. Okay, so this thing is known as what? The reduced mass of a system. Okay, m1 m2 upon m1 plus m2. So now if you want to find out moment of inertia of two objects about the center of mass, then what you will take is you will take the reduced mass of the system, that is m1 m2 divided by m1 plus m2, okay, and distance between two objects is suppose L, then the moment of inertia is just mu multiplied by L square, okay, mu is the reduced mass, right? So you can write moment of inertia I is just equal to mu multiplied by L square. So what is mu? Mu is the reduced mass of two objects, okay. So now an example of this is the one that we saw, the two masses, two objects connected at the ends of a rod, okay, a light rod. Then another example, moon and earth, right? Moon revolves around earth. So what's the moment of inertia of the system about the center of mass? Again, it is two objects separated by some distance, okay, that is radius of revolution of moon. So therefore, what would be moment of inertia? It is mu multiplied by r square, right? So is this thing clear, everyone? Answer is option A. Okay, so now onwards, just remember this result: moment of inertia of two objects about an axis which passes through the center of mass, it is just mu multiplied by L square, right? Very simple. Okay, then let's see next one. Two bodies have their moments of inertia I and 2I respectively about their axis of rotation. If their kinetic energies of rotation are equal, their angular velocity will be in the ratio. So you have two objects having mass I and 2I respectively, and about the axis of rotation, kinetic energies are equal. Then what's the angular velocity? Very simple question, right? So E1 is equal to E2. E1 is half of I1 omega square. E2 is equal to half of I2 omega square. So cancel out half and half. I1 is I2 is equal to 2I, right? I2 is equal to 2I. So this is I times, okay, there will be omega 1 and omega 2, right? So I times omega 1 square is equal to 2 times I, this is the moment of inertia, I2 of the second body, times omega 2 square. So then I and I gets cancelled out, and you get omega 1 by omega 2 square is equal to 2, right? So omega 1 square divided by omega 2 square is equal to 2. Therefore, what's the ratio of omega 1 is to omega 2? So omega 1 is to omega 2 is just root 2 is to 1. Okay, so just compare kinetic energies and find out the answer. Very simple question, right? Okay, good, very simple. Let's see next one. A ring of mass m and radius r rotates about an axis passing through its center and perpendicular to its plane with angular velocity omega. Its kinetic energy is, so that is a ring of mass m and radius r. So what is the kinetic energy? It's very simple. It is half of E is equal to half of I omega square. Okay, so that is half of I is mr square times omega square. This is a very old question. At least I don't expect this question in 2024. Okay, so this is the answer anyways, right? Very simple. So these were basic questions based on a basic topic, moment of inertia. Now we want to find out moment of inertia of several bodies. Okay, so we need to remember this formulae. Which formulae? These formulae we need to remember. Okay, moment of inertia of several bodies, several objects. This table you need to remember, right? And then there will be some topics built on that. Okay, so let's talk about the next topic, that is radius of gyration or gyration, okay, in whatever way you pronounce it, radius of gyration. Now what is this thing? So suppose this is a body and it's rotating about this axis, passing through suppose this is a body and it's rotating about this axis as shown in the figure. Okay, it can pass through any point, right? So then now the moment of inertia of this body, it is given by this formula. It is summation of mi ri square, right? Summation of mi ri square. This is moment of inertia. Then now suppose I want to replace this body. Okay, I want to replace the body with one point particle, point sized particle. So at what distance should I keep that particle so that it will have same inertia, same moment of inertia as that of the body? Okay, that distance is called as radius of gyration. Okay, so suppose I have this body and I want to replace it by a point sized particle. Okay, a particle having mass equal to mass of the body, right? Then at what distance should I keep that particle whose mass is equal to mass of the body so that that particle will also have same moment of inertia as that of this body for this axis of rotation? Then at what distance should I keep that particle? That distance is known as radius of gyration, k. Right? This is clear? Everyone? Yes, no? Okay. Now you find out moment of inertia of the body using either this formula or using integral of r square dm, using this or that formula. Then how do we find the radius of gyration or radius of gyration? So let's take an example. I want to find out the radius of gyration of this thin rod, suppose. Then what should I do? I want to replace that by a point sized particle having mass equal to mass of the rod. Okay, that is capital M. Then what would be moment of inertia of this one particle? It is just its mass multiplied by distance square, mk square, right? It is just equal to mk square. Okay, so now we know the moment of inertia of this rod is equal to what? ml square divided by 12, right? Moment of inertia of the rod is just ml square divided by 12. We know that. Then I want to find out its radius of gyration. So what I do is I write mk square. Okay, I replace this by this point sized particle kept at distance k. So moment of inertia of this one would be mk square. So mk square is just equal to what? The moment of inertia of this body, which is ml square divided by 12. Cancel out m and m, then what do you get? K square is L square divided by 12, and therefore K is equal to L divided by root of 12. That is, K is equal to L upon 2 root 3. Okay. Is this thing clear? Okay. Very simple. Then next, let's see ring. A ring having mass m. I want to replace the ring by a point sized particle. Okay, where should I keep that particle to have same moment of inertia? So that is known as radius of gyration. That distance is known as radius of gyration or gyration. Okay, sometimes I myself call it gyration, sometimes I call it gyration. Okay, never mind. So radius of gyration, it is so moment of inertia of this particle would be mk square. Mk square is equal to mr square. Cancel out m and m, right? Because moment of inertia of the ring is just mr square. So cancel out m and m. Then what do you get? You get k is equal to r. K is equal to r, right? Very simple. Then for a disk about this axis of rotation which passes through its center, okay, moment of inertia is mr square divided by 2. And now suppose I want to replace this disk by a point sized particle having same mass as that of mass of the disk. Then its moment of inertia is mk square, right? moment of inertia of that particle would be mk square. So mk square is mr square divided by 2. Cancel out m and m. Then what do you get? K square is r square by 2, and therefore k is equal to r divided by root 2. Right? This thing is clear, everyone? Okay. Good. Then now what is significance of this thing? What is the significance of radius of gyration? So now you can consider these two wheels. Okay, one is a solid wheel and one is this usual wheel with spokes, right? So then suppose the radius of this wheel and this wheel, a disc shaped wheel and a ring shaped wheel having spokes, okay, suppose their radius is equal, right? Then now suppose radius is equal, so the radius of gyration will give you distribution of mass about the axis of rotation. Okay, how close or how far the mass is distributed about the axis of rotation, that will be given by the radius of gyration or radius of gyration. Is this thing clear? Yes, no? So whose radius of gyration would be more? First ring, first disc or first wheel or the second wheel? First one is disc, second one is like a ring. So approximately you can say radius of gyration of this one is r, for this one is r upon root 2, right? So for disc shaped wheel, the mass is distributed closer, more close to the axis of rotation. Yes, no? Okay, this is clear, yes or no? Okay, so what does radius of gyration tell you? It tells you the distribution of mass from the axis of rotation, whether the mass is distributed closer or away from the axis of rotation. Okay, so that is radius of gyration. Then now suppose we know moment of inertias of these bodies, like these regular shaped bodies, a thin rod or a ring or a disc, for specific axis, for natural axis, let's say. So what is the natural axis? For a thin rod, natural axis would be an axis passing through the center perpendicular to its plane. Okay, natural axis means symmetric axis, okay, about which, or natural axis means an axis passing through the center of mass and perpendicular to plane of the body. Okay, then for the ring, its axis passing through the center of mass perpendicular to plane of a ring. For a disc, an axis passing through center of the disc perpendicular to plane of the disc. So suppose you know the moment of inertia of these bodies about this axis which passes through the center of mass, then you want to find out moment of inertia about some other axis, and you can relate that other axis to the first axis, right? Then how will you find it? Okay, so every time it's not advisable to do the integration, right? Dm multiplied by r square integral. Okay, so suppose you have this thing, moment of inertia about this axis, which is equal to what? ml square by 12. Okay, for the thin rod, and you want to find out moment of inertia about this axis. What will you do? So for that we have specific theorems called as a parallel axis theorem and a perpendicular axis theorem. Okay, so let us talk about them. What is a parallel axis theorem and what is a perpendicular axis theorem? Okay, so first one, let's talk about the perpendicular axis theorem, right? So this perpendicular axis theorem is only applicable to laminar bodies, planar objects. Okay, So bodies which you can keep in a plane, okay, or on a plane, flat surface, right? For an example, a ring or a disc, okay, a ring or a disc, these are planar objects, okay. A thin rod is also a planar object, you can keep it in a plane, right? So these are planar objects. So this is applicable to planar objects. It's not applicable to solid objects. So don't try to apply perpendicular axis theorem to solid objects. Okay, for something like what? Um, okay, something like this bottle. You cannot apply the perpendicular axis theorem to the bottle, right? This is not a planar object. Okay, so for solid objects, it's not correct. I mean, we cannot apply it, and for planar objects only we can apply the perpendicular axis theorem. Now let's understand what is the theorem. So suppose you have moment of inertia of this object about an axis passing through its center of mass and perpendicular to its plane is known. Moment of inertia of this object about an axis passing through the center of mass and perpendicular to its plane is known, okay, and suppose that is equal to I suffix z, okay, Iz. So that is equal to sum of moment of inertia about two axes in its plane, okay. But what are those two axes? So those two axes are x and y. What does that mean? So those two axes also pass through the center of mass and they lie in plane of the body, and those two axes are perpendicular to each other. Actually, if you see, all three axes are perpendicular to each other, okay. So Iz is equal to Ix plus Iy, right? Is this thing clear, everyone? Okay, so Iz is equal to Ix plus Iy. So you know, what do you know? You know the moment of inertia of the body about an axis which passes through its center of mass and which is perpendicular to its plane, okay. Then you can find out the moment of inertia of the body about axes which are passing which are in plane of body, okay, which lie in plane of the body, right? So and those two axes also pass through the center of mass and they are perpendicular to each other, right? So this Iz, the moment of inertia about axis which is perpendicular to plane of body and passing through the center of mass is equal to sum of moment of inertias of the body about two axes. What are those two axes? They lie in the plane of body, they are in the plane of body, okay, and they are perpendicular to each other and they also pass through the center of mass, okay. So Iz is equal to Ix plus Iy, right? So now there is a proof of this, but we'll not go into the proof. We'll just see examples based upon this thing. Okay, so just see, find moment of inertia of a ring about a diametric axis. So what do we know right now? We know that moment of inertia of a ring about an axis passing through its center and perpendicular to the plane. Okay, this we should know, right? So that is mr square, we know that, okay. So that is our Iz, right? That is our Iz. So now I want to find out Ix or Iy because both are same, okay. This x-axis is also passing through the center, that means it passes through the center of mass and it is in plane of the body. Y-axis is also passing through the center of mass, it is in plane of the body. Both are equal, right? This is also a diameter, this is also a diameter, okay. Then so what I can say is Ix is equal to Iy and it's equal to Iz. Then we apply the perpendicular axis theorem, which is very simple. So Iz is equal to Ix plus Iy, okay. Iz is equal to Ix plus Iy. So Ix is equal to Iy and that's equal to, suppose, I suffix d. What does this mean? It is moment of inertia about a diameter, d for diameter, right? So diametric axis, okay, x and y, they are diametric axes. So Ix is equal to Id, Iy is also equal to Id. Id means moment of inertia about diameter. So Id plus Id is 2Id, right? 2Id is equal to mr square. So we know moment of inertia of ring about the z axis is mr square. Okay, so mr square is equal to 2Id, means Id is equal to mr square divided by 2, right? So you found the moment of inertia of this body, the ring, about a diametric axis. It is mr square divided by 2. Is this thing clear, everyone? Okay, so this is how we apply the perpendicular axis theorem. Let's take another example. Okay, so here you can just say that it becomes half, right? Moment of inertia about perpendicular axis, an axis which is perpendicular to plane of body, but it is passing through the center. It is suppose mr square. Then moment of inertia about diametric axis become just half. Okay, that's very simple, right? Similarly, for a disk, we know moment of inertia of a disk about perpendicular axis passing through the center is what? It is mr square divided by 2. Moment of inertia about diametric axis will become half of that, so that becomes mr square divided by 4. Okay, so next let's talk about the parallel axis theorem. Parallel axis theorem. So what is this? So again, suppose you know the moment of inertia of a body about an axis which passes through its center of mass. Okay, and that is suppose I suffix c, right? Now this one is applicable to any kind of body, laminar, okay, or a solid body, every kind of body. So what do you know? You know moment of inertia of the body about an axis which passes through the center of mass. Then now you want to find out moment of inertia of this body about an axis which passes through some point, doesn't matter which point, okay, but it is parallel to this axis. To which axis? The axis that passes through the center of mass. Okay, so you know moment of inertia about this axis, you call it IC, okay, because this axis passes through the center of mass. Then you want to find out moment of inertia about this axis, suppose, which passes through point O, some point O, okay, but about an axis which is parallel to this first axis. Then how can you find it out? So it's very simple. So I suffix O is suppose the moment of inertia about this parallel axis, and it is just equal to IC plus mh square. Okay, what is h? H is the mass of the body, m is the mass of the body, and h is the perpendicular distance between these two axes, right? M is mass of the body and h is the perpendicular distance between these two axes. Is this thing clear? Yes, no? Everyone? What do you know? You know moment of inertia about this axis which passes through the center of mass. You know that. And you want to find out moment of inertia about the axis which is parallel to this first axis. Okay, and it passes through any point, that does not matter. It can be inside of body, that point can be interior point, it can be exterior point too. Okay, so then you have IO is equal to IC plus mh square. M is mass of the body, h is distance between these two axes, perpendicular distance between these two axes, right? So again, we'll not go into the proof of this thing. Okay, and then let's see some examples. So find the mi of a thin rod about an axis passing through its edge. Okay, find moment of inertia of a thin rod about an axis which passes through its edge, right? So this is suppose thin rod. What do you know? You know its moment of inertia about an axis which passes through the center of mass, and it is ml square divided by 12, that you know, right? So then draw a parallel axis which passes through one of its edge. Okay, so this is point O, and you want to find out its moment of inertia about this axis, so that is IO. That is suppose IO. So you know the formula, IO is equal to IC plus MH square, right? IO is equal to IC plus MH square. Yes, no, right? What is IC? IC is ml square divided by 12. Okay, then what is H? H is the distance between these two axes. So it is just equal to L by 2, right? This distance is just equal to L by 2, half of the length of this rod. So put H is equal to L by 2. Then you have ml square divided by 12 plus m into L by 2 square. L by 2 square is L square by 4, right? It is L square by 4. You add it up, then what do you get? You get IO is equal to ml square divided by 3, right? Because ml square by 4 can be written as what? 3 times of ml square divided by 12, right? Multiply by 3, divide by 3, because you want to make this denominator same. So 4 times 3 is 12, multiply numerator by same, okay, by the same. So 3 ml square divided by 12 plus ml square by 12 is 4 ml square divided by 12, means ml square divided by 3, right? So is this one clear? Yes, no? Okay, very good. Then let's see next one. Find moment of inertia of a ring about tangential axis perpendicular to its plane. About a tangential axis. So this is a tangential axis and it is perpendicular to its plane, right? So you know IC for a ring, it is mr square. Moment of inertia about an axis which passes through the center of mass and perpendicular to plane of the ring is mr square. You know that, okay? And you want to find out moment of inertia about a parallel axis, right, which is also perpendicular to plane of the ring. So write I naught is equal to IC plus MH square. IC is MR square. And what is H? H is also equal to R. Okay, so MR square plus MR square. So I naught is equal to 2 MR square, right? That's very simple. Okay. Oh, just 1 second. Okay, but while proving this theorem, there is one important point. Okay, it comes in the proof of this thing that I want to explain. Principle of moments of masses. Now what is this thing? Okay, so center of mass, the position vector of center of mass of a body can be written as m1 r1 bar plus m2 r2 bar plus so on and so forth up to plus mn rn bar divided by mass of the body, right? This is center of mass of the body. So then what is moment of mass? Moment of mass is mass multiplied by position vector of the mass. Okay, so suppose you take some mass over here. What is its moment of mass? It's mass multiplied by its position vector. Okay, mass is suppose m1, position vector is r1 bar. So this thing is the moment of mass, right? Now suppose you want to find out moment of all masses about the center of mass, means you will measure the position vectors from the center of mass. Okay, suppose you want to find out moments of all masses, that means m1 r1 bar plus m2 r2 bar plus so on and so forth up to plus mn rn bar. This is sum of moments of all masses, right, about the center of mass. That means you need to keep center of mass at the origin. Is this thing clear? Yes, no? Okay, So that's why the sum will be equal to 0. Okay, that's why this sum will come out to be equal to 0. Okay, so this is one way of understanding this. There is another way. So you can say, what is center of mass? It is point of the body at which whole mass of the body is concentrated, right? Point of the body at which whole mass of the body is concentrated. That means, suppose this is that point, then mass of the body must be symmetric about this point, around this point, right? So whatever mass is there towards left, same mass would be, same amount of mass would be there towards right at the same distance. Okay, yes, no. So if this distance is negative, this distance would be positive. Okay, if this distance is negative, this distance would be positive. So m times x plus m times minus x will give you what? 0. Okay, and that's why moment of all masses about the center of mass must be equal to 0. Okay, so sum of moments, not moments, sum of moments of all masses about the center of mass is equal to 0. And what does this mean? It means that all three coordinates would be equal to 0. I mean, so summation of mi ri bar is equal to 0 means summation of mi xi, okay, x moments are 0, right? So if this thing is 0, that means all components are 0, all components of moments are 0. So moments about x axis are 0, right? Mi xi is 0, summation of mi yi is equal to 0, and also summation of mi zi is equal to, I goes from 1 to n, this thing is also equal to 0. This thing is clear, everyone? Sum of moments of all masses about the center of mass is 0. So this thing comes in the proof of the parallel axis theorem, and without this the parallel axis theorem cannot be proved. Okay, so in short, let me just explain the parallel axis theorem, the proof of parallel axis theorem, because then you will remember this thing. Okay, so proof is simple. So suppose I want to find out, I want to prove that IO is equal to IC plus mh square. What will I do? I will take some mass, some object, suppose. Okay, so this is small piece of the body. What would be its moment of inertia about this axis? Okay, let's call this axis O dash. So then its distance from this axis is RO. So moment of inertia will be dm is the mass, dm multiplied by RO square. What will be its moment of inertia about this axis which passes through the center of mass? It will be dm multiplied by this distance square, that is dm multiplied by rc square. Okay, dm multiplied by rc square. Okay, so moment of inertia about this one is dm multiplied by RO square. Okay, so that is dio is dm multiplied by RO square. So now if you see RO square here in this diagram, so now it can be written as, see, this distance square plus this distance square, right? Using Pythagoras theorem, it can be written as OM square plus this point is suppose P, PM square. Okay, RO square is OM square plus PM square, right? Then now you can write this OM as OC plus CM, right? OM can be written as OC plus CM. Okay, so you have OC plus CM square plus PM square is this distance square. Okay, so that is DIO, right? So then you have you just expand this, so you get OC square plus 2 times of OC into CM. Okay, OC plus CM square, right? OM square is OC plus CM square, so that is OC square plus 2 times of OC into CM plus CM square, right? And then you have plus PM square, So then see what do you get. Cm square plus Pm square is what? It is Rc square. Okay, Pc square, or you can say it is Rc square, right? So this is equal to Rc square. Then what is OC? So OC is distance between these two axes, so that is equal to h, right? Distance between two axes is equal to h. So square of that is h square. So you can already see you're going towards the result. Okay, so DIO is moment of inertia of the small mass about which axis? About an axis passing through O. And the parallel axis theorem says it is equal to IC, moment of inertia about center of mass, okay, plus m times dm times h square, because you're taking for that small mass, right? You're finding moment of inertia for the small mass, okay. So DIO must be equal to DIC plus m times h square, dm times h square, right? Okay, this is clear? Yes, no? Okay, good. So then this is DIO. It is OC square plus 2 times of OC into Cm plus RC square, and OC square is h square. The distance between two axes is h, right? So then this distance OC is equal to h, distance Cm is equal to suppose x, okay. Then this is moment of inertia of the small mass DIO. You integrate that over whole body, okay. So this is moment of inertia of the small mass dm. You integrate that over the complete body, then what do you get? So DIO integration of that would be the moment of inertia of full body, complete body, about axis passing through this point O, right? Then it is equal to, see, if you integrate this thing, dm times rc square, then what do you get? You get moment of inertia about which axis? About an axis passing through the center of mass, and that axis is perpendicular, sorry, it is parallel to this axis, okay. These two axes are parallel. If you integrate this thing, dm times h square, then what do you get? H is a constant, because once you fix those two axes, distance between them is a constant, okay. So h is a constant. Then integration of that, okay. So integration of dm is just m, capital M. So you have m multiplied by h square, okay, m multiplied by h square. So you got integration of dm times h square, which will be capital M times h square, integration of this term, okay, dm times rc square. So dm is that small mass, and rc is distance from the axis passing through the center of mass, okay. So this is moment of inertia of the small mass about the axis passing through center of mass. If you integrate that, you get moment of inertia of complete body about the axis passing through the center of mass, right? Okay, so this is DIC. If you integrate that, you get IC. Now what about this term? Okay, this last term. So we have 2 times of dm multiplied by h times x. H is the constant. So if you integrate that, you can take this 2 and h outside. So integral of dm times x. So here comes that point. So see, integral of dm times x. So this mass is dm, okay. Now you took this line, suppose, okay, this is the line perpendicular to these two parallel axes, okay. So now this mass, now what you do, suppose you call it x-axis, right? Suppose you call it x-axis. Now this mass is distributed little bit towards right of the center of mass, you can say, right? Is this thing clear? So suppose you have this mass, you call this one x-axis, okay. This is an axis passing through the center of mass, okay. So then you can say this is the origin, right? You can consider center of mass is at origin. So if there is some some mass towards right hand side, there would be same amount of mass towards left hand side of the center of mass, right? So therefore if you integrate this x dm, if you integrate that, that integration would come out to be equal to 0, because we know that moment of all masses about the center of mass is equal to 0. Okay, so this thing becomes 0, and therefore you have IO is equal to IC plus mh square. So is this thing clear, everyone? Yes, no? Okay, so now, okay, very good. So at this moment, the proof doesn't have any significance for us, but this thing, sum of moment of all masses about the center of mass is equal to 0, there can be a question solely based on this thing only, right? There can be a question just like this: what is sum of moment of all masses about the center of mass? Okay, and they can give you 4 options. All right, because this is a concept. Okay, so we need to remember all the concepts. Sorry. All right, so then let us see some problems based upon this thing, the radius of gyration and parallel and perpendicular axis theorem. So ratio of radii of gyration of a circular disc to that of circular ring, each of the same mass and radius around their respective axis. Respective axis means natural axis. Natural axis means passing through center of mass perpendicular to plane of the body. Okay, that is respective axis. Right. So ratio of radius of gyration of circular disc, so r for disc to that of r for ring of same mass. Okay, not r, radius of gyration, no, so we denote it by k. Okay, and they have same mass, same radius. So tell me, what's the answer? Option D. Let's check. For a disc, it is equal to r divided by root 2, right? And for the ring, the radius of gyration is just equal to its radius. So r gets cancelled out and it is just 1 upon root 2. That's very, very simple. Option D. Right, very simple. Let's see next one. The ratio of radii of gyration of the circular disc about tangential axis. This is different. Tangential axis in plane of the disc and circular axis, circular ring of the same radius and mass about the tangential axis in plane of the ring is. Okay, so you have a disc like this and you have a ring. So you want radius of gyration about tangential axis. So this is an axis passing through the center in plane of the disc. Okay, so you know now moment of inertia about this axis. How much is it for the disc? Tell me. Anyone? Mr square divided by 4. Very good. No, mr square divided by 4. Okay, so for the perpendicular axis it is mr square divided by 2. Right? Yes, no? Okay, good. So for this axis, diametric axis, moment of inertia of disc or ring, it is just half of the moment of inertia about the perpendicular axis passing through the center. Okay, passing through the center. So if that is I, this would be I by 2. So what is I for disc? It is mr square by 2. and therefore what is moment of inertia about diametric axis? It is I by 2 means mr square divided by 4. Okay, so moment of inertia about diametric axis for id for, let's say, disk. Okay, so this is diametric axis. Okay, let's say this is about the center. IC for disk is equal to mr square divided by 4. Then what would be moment of inertia about this tangential axis in plane of the disk? So just apply parallel axis theorem, and therefore you get IT is equal to, okay, this IC for disk plus mh square. So what is the distance? It is r, that is mr square. Okay, so mr square by 4 plus mr square, and that is what? 5 mr square by 4. This is IT for the disk, or let's just call them 1 and 2. So IT1. Similarly, what would be IT for the ring? So that's simple. What is ID? Okay, option C. Let's check. What is ID? ID is mr square divided by 2, right? And then you have IT for the ring. It's equal to mr square divided by 2 plus mr square. So that is 3 by 2 mr square. 3 by 2 mr square. Okay. So then you found the moment of inertia, but what do you want? Basically, you want the ratio of radius of gyration. Okay. So radius of gyration, to find radius of gyration, either you equate that with mk square. Okay. For the disk, mk1 square is equal to 5 by 4 mr square. So gets cancelled, and for the ring you have k2. Okay, so k2 square is 3 by 2 mr square. M times k2 square is 3 by 2 mr square. Again, you cancel out mr square everywhere. Okay, what do I mean by that? Just divide this thing by that thing. So mr square and mr square, will get cancelled out, and then you have k1 by k2 square is equal to 5 by 4, and dividing by 3 by 2 is multiplied by 2 by 3. So this thing is 2, 5 by 6, and then if you want k1 by k2, it's just square root of that. Square root of 5 by 6 is the answer, right? So it is option C. Good. Okay, so this thing is simple. Yes, no? Everyone? Right, Selva Kumar, this is clear?
Yes, sir.
Okay, good. Let's see next one. Moment of inertia of a uniform circular disk about a diameter is I. Its moment of inertia about an axis perpendicular to its plane and passing through point on the rim will be. Moment of inertia of uniform circular disk about diameter is I. Okay, so this is given. So moment of inertia of a disk about the diameter is I. Right, so ID, you know, ID is equal to I, it's given, and that is equal to mr square divided by 4 for a disk, right? You know that IC is equal to mr square upon 2, and about the diameter it just becomes half of that. Okay, using the perpendicular axis theorem we saw that. Okay, so ID is mr square by 4, and then its moment of inertia about an axis perpendicular to its plane and passing through point on the rim will be. Okay, so right, this is I, and you want moment of inertia about perpendicular to plane axis which is perpendicular to plane and passing through the point on the rim. So you want it about this tangential axis, right? Then you have moment of inertia about this axis is IC. Okay, so IT would be equal to IC plus mh square using the parallel axis theorem. Okay, option C. Let's check. So IC is mr square divided by 2 plus mh square. So that is h is also equal to r. This is mr square. Okay, so this thing is 3 by 2 mr square, right? And then this is IT. Okay, and therefore now here from this, what can you say? You can say mr square is equal to 4i, right? Just take that 4 on other side. Mr square is equal to 4i. So IT is equal to 3 by 2 mr square, means 3 by 2 times of 4i. Okay, so 3 times 4 is 12, or 12 by 2 is 6i. Yeah, so Yamini told the answer. Very good. So it's option C. Right, this is simple. Yes, no. You just have to do some adjustment. There is nothing. Okay, Nikita, this is clear? Okay, good. All right, let's see next one. The moment of inertia of a disk of mass capital M and radius r about an axis which is tangential to the circumference of the disk and parallel to its diameter is. Okay, let me read it once, because I just read and I didn't understand what did I. Okay, read. The moment of inertia of a disk of mass m and radius r about its axis. Its axis means about an axis which is tangential. Okay, moment of inertia of the disk of mass m and radius r about an axis which is tangential to the circumference of disk and parallel to its diameter. Okay, so you have disk and you want its moment of inertia about an axis which is tangential but it is parallel to the diameter. So tangential but parallel to the diameter. Okay, so moment of inertia about diameter, you know, for the disk it is mr square by 4. Okay, and you want moment of inertia about tangential axis. Actually we found it in earlier problem, right? So IT is equal to ID plus mh square. That means h is also equal to r. So IT is equal to ID, which is mr square by 4 plus mr square. That is 5 by 4 mr square, right? So again, very simple problem. Okay, but it can come. It can means a problem like this. Okay, simple one, right? Let's see next one. Moment of inertia of a uniform circular disk of radius r and mass m about an axis touching the disk at its diameter and normal to the disk is. Touching the disk about the diameter and normal to the disk. There is no such axis. Touching the disk at diameter and normal. Okay. No, what is this? Okay, so this is diameter. Touching the disk at diameter and normal to the disk is. Maybe, just maybe, they just want to say that about a normal axis, tangential, right? Otherwise, what will it be? touching the disk at diameter and normal to the disk. Okay, so see, I don't know what does this mean, right? Touching the disk at diameter and normal to the disk. So I think they want to say this axis. Okay, which one? A tangential axis. It touches the disk, right? And you can say at diameter because it passes through this diameter, some diameter, right? Okay, so it is this axis. All right, so let's find out moment of inertia about this axis, because question is little bit, the framing is little bit weird. Okay, so what would be IT? So IT just equal to IC plus mh square, right? And what is IC? IC is mr square. Okay, so it will be mr square. No, for the disk it will be mr square divided by 2. mr square divided by mr square divided by 2 plus mr square. So it's 3 by 2 mr square. So maybe they are asking about this axis only. So it will be option D. Right. So this thing is clear. Or does somebody have any other opinion about this one? Yes, anybody? Bhanu, Yamini, or anybody? What do you think? It is this axis or something else? Touching the disk at its diameter and normal to the disk. I think it is this axis only. Any other opinion? All right, so they could just say it's tangential axis perpendicular to plane of disk. Okay, that is how you should say. Anyways, let's see next one. A thin rod of length L and mass M is bent at its midpoint into two halves. Okay, a thin rod of length L and mass M is bent at its midpoint into two halves so that the angle between them is 90 degrees. Angle between two halves is 90 degrees. The moment of inertia of the bent rod about an axis passing through the bending point and perpendicular to plane defined by two halves. Okay, so that is fine. You take a rod like this and you bend it into two halves, okay, at 90 degrees. Right, so then you want to find its moment of inertia about a perpendicular axis like this. Okay, you want to find its moment of inertia about this perpendicular axis. So then mass of this part is suppose m dash, mass of this part is m dash. Okay, so then you know for this mass or for this much rod, okay, let's say these are two separate rods. So for this one it is an axis passing through the edge, and we have found what is moment of inertia of a rod about an axis which passes through the edge of the rod. It is ml square divided by 3, right? So mi of a rod about axis passing through its edge, is, it is equal to ml square divided by 3. Okay, but here mass is m dash, length is also l dash. Okay, so for this one it will be m dash l dash square divided by 3, and for this one also it will be m dash l dash square divided by 3. There are two rods, right? So let's assume that these are now two separate rods. So what will be total moment of inertia? M dash l dash square divided by 3 plus m dash l dash square divided by 3 and then just put the values. So it is 2 by 3, okay, 2 m dash l dash square divided by 3, right? So that is just, what is m dash? It's m by 2. What is l dash? It's l by 2. Okay, so this 2 gets cancelled. L by 2 square is L square divided by 4. So 4 times 3 is 12. So again it is ml square divided by 12. Okay, so this is the answer. Right? Is this thing clear? Yes, no? Okay, it is ml square divided by 12. Okay, good. So now see, this thing can be solved, okay, I mean just by thinking. So suppose you have this rod and you want to find out its moment of inertia about this axis, right, about this axis. Then now how will you find moment of inertia? Summation of mi ri square. So see, there is some distribution of mass on this side, some distribution of mass on this side. Okay, suppose you bend this one, still the distance of these masses from the axis of rotation will not change. Is this thing clear? Yes, no? You bend the rod, okay, still the distance of these masses from the axis of rotation will not change. You are bending it, right? You are not changing the distance. Suppose you bend this part, okay, so this part is kept like this or it is kept like this. Okay, can you see that? Suppose you bend this part, so this part is kept like this or it is kept like this. Still distance of these masses from this axis will remain same. Yes, no? Okay, so there is no need to change the moment of inertia. Moment of inertia will remain same. So earlier if it was ml square by 12, now also it will remain ml square divided by 12. Okay, yes, no? But if you bend it like this, suppose it was horizontal, if you bend it like this, then it will change, because perpendicular distance of masses will change in that case. Okay, everyone, good. So if you understand this point, that's very good. Otherwise also it's not that difficult, but if you understand this one, it will save a lot of time, right? Because otherwise we need to solve this. Anyways, good. So then let's see next question. 4 identical thin rods, each of mass m, capital M, and length small l, form a square frame. Okay, square frame. Moment of inertia of this frame about an axis through the center of square and perpendicular to its plane is. Okay, so you have 4 rods, they are forming a square frame and you want to find its moment of inertia about an axis through the center of the square and perpendicular to its plane. Okay, so let's find it out. So you have a square frame, let's say like this. So there are 4 rods, okay, and you want its moment of inertia about which axis? The axis which passes through the center, right? The axis which passes through the center of this frame. Okay, so this is that axis. Okay, so now see, if it passes through center, what is the distance of perpendicular distance of each rod from this axis? It is just this much, L by 2, right? This is L by 2, and we know moment of inertia of the rod about this axis. Which axis? About an axis passing through its center of mass, that means its midpoint. Okay, you know that. So this is IC. Let's just think about one rod. So for this one it is IC and this is IO, and you know IO is equal to IC plus MH square. What is H? H is equal to L by 2, right? So IO is equal to IC plus MH square. H is equal to L by 2. This distance is L by 2, right? So just put the values. So this is ML square divided by 12 plus ML square, ML by 2 square. So that means ML square divided by 4, ML square divided by 12, and this thing is ML square divided by 4. That means 3 ML square divided by 12, right? Multiply by 3 divide by 3. So 3 ML square by 12 plus ML square by 12 means 4 ML square divided by 3. Okay, 4 ML square divided by 12. That means ML square divided by 3, right? So just like what we found for the case of moment of inertia about the edge of the rod, it's ML square divided by 3. But this is for one rod and you have 4 such rods. Therefore, MI of frame is equal to 4 times of IO, that is equal to 4 times of ML square divided by 3, 4 ML square divided by 3. So it is option D. Okay, this is clear? Yes, no? Okay, very good. Let's see next one. There can be a lot of questions. Okay, similar questions. The moment of inertia of a thin uniform rod of mass m and length L about an axis passing through its midpoint and perpendicular to its length is IO. Okay, so passing through the midpoint and perpendicular to its length is IO. Its moment of inertia about an axis passing through one of its ends and perpendicular to its length is. Okay, there is nothing in this one. This is simplest of all. So they say that moment of inertia about this axis is IO. So what we called IC earlier, they are calling that one as IO, right? So it is, we know, ML square divided by 12, but we don't want that thing too. Okay, that is not required because they have written IO in all of the options, right? And you want its moment of inertia about this axis, okay, which is passing through one of its ends. So let's suppose this is IO dash, okay, IO prime. So IO prime would be equal to IO plus MH square using the parallel axis theorem. What is H? H is L by 2. So it is IO plus M into L by 2 square. That means ML square divided by 4. So this is the answer. Okay, this one is very simple, right? Okay, let's see next one. Moment of inertia of uniform circular disc is maximum about an axis perpendicular to the disc and passing through. Okay, so axis passing through which point? A, B, C, D. Tell me, this one is very simple. You have this I'm sorry, the disc, and this is point A. Okay, for point A, you know the moment of inertia of disc is mr square divided by 2 and you call it IC, right? This is moment of inertia about this axis would be IC. Then you have some other point. This is point, let's say C. Okay, it's at this much distance. So moment of inertia about an axis passing through this point C would be equal to I suffix. Okay, so let's say this is IA, okay, and this is point C. Oh, This is point C, this is point A. What will be IC here? So IC would be equal to IA plus m multiplied by h square, this distance square, right? Okay, let's call this distance as h1. Then see, point C is away from point A compared to that of point D. That means this h would be greater for point C, but for B it would be greatest. Okay, so what is point B? Where is the point B? Point B is here at the edge, right? So not at this edge, some other edge you can say, but it's same thing. Okay, so point B is here. So for point B, how much is this distance? This distance is equal to r, right? So what is IB? IB is equal to moment of inertia about the center, that is IA plus m times h square. So let's say h2 square, but this distance would be greatest, right? This is the greatest distance, and that's why moment of inertia about B is greatest. Okay, it is as simple as that, right? Yes, no? Okay, so very simple question, right? So the questions on moment of inertia cannot be difficult. Okay, that's what I think. Let's see next one. 3 identical spherical shells. Okay, these are spherical shells, each of mass m and radius r are placed as shown in the figure. Okay, so this is 1, this is 2, and this is 3. Consider an axis x dash shown here, which is touching the two shells and passing through the diameter of third shell. Okay, the moment of inertia of system consisting of these 3 spherical shells about x dash axis is. Okay, tell me. So what is moment of inertia of a thin spherical shell? About an axis which passes through its center and it's perpendicular to its plane. So it is 2/3 moment of inertia of a shell about an axis which passes through its center. An axis which passes through the center, it's option B, let's check, 2/3 mr square. Okay, then now you have this one shell for which the axis is passing through the center. For the other two, it is tangential axis, right? For the other two, it's tangential axis. So then for tangential axis, we need to find out the moment of inertia. Okay, so moment of inertia for a tangential axis like this would be equal to what? Moment of inertia about axis which passes through the center, IC, okay, plus mh square. This is IC, and distance is r. So moment of inertia about this tangential axis is equal to 2/3 mr square. So IC plus mh square. So 2/3 mr square plus mr square. Okay, so this can be you can say this is 3/3 mr square. So 2/3 mr square plus 3/3 mr square means it is equal to, right, 2/3 plus 3/3 means 5/3 mr square. Okay, so therefore what will be total moment of inertia? So you have one one spherical shell for which axis passes through the center, and 2 for which axis passes through the tangent, and therefore total moment of inertia will be equal to IC plus 2 times of IT. Okay, so let's just put the values. Let us just put the values there, and therefore what you get, moment of inertia is equal to 2/3 mr square plus 2 times of 5/3 mr square mr square you can take common. So 2 plus 10 means 12/3. 12 by 3 mr square. That is 4 mr square. Right, so it is option B, right? So Nikita said option B, right? It's option B, correct. Okay, so this is clear. Yes, no? Everyone? Right. So this is how we solve the problems based on moment of inertia. Okay. So now there are chances that there would be a problem based on parallel or perpendicular axis theorem. Okay. This topic is important in this chapter. See, the chapter itself is important because this one is big chapter. Okay, and the trend is, so we can't say what will be the future, right? But trend is that they ask some questions, at least 2 questions based on this chapter. So we can expect that there would be at least 2 questions based on this chapter. Okay, and 1 question I think should be based on this topic. Okay, but we don't know. So we'll do complete chapter, right? We'll understand every topic and it is not difficult. Okay, so we should do this. So trend is like they ask at least 2 questions, 2 to 3 questions based on this chapter. Okay, so if we follow the trend, we can expect again 2 to 3 questions based on this one. Okay, all right. So we'll stop at this point and tomorrow we'll see the next part.